I'm very excited to be here. It's great that we're shipping Filecoin. It's great that we're already on mainnet. And what's even more amazing is that even though mainnet is mostly running with Lotus right now, there are 3 other implementations that are very close to being part of that network as well. So I'm going to talk a little bit about why why having multiple implementations is important to verify the correctness of Filecoin and to make the Filecoin protocol itself and to make the network robust. And also, I'm going to talk about some tooling that we've developed to make sure that all these implementations are able to interoperate and to make sure that we can conformance test them according to a specification. So our agenda for today is going to be, first of all, I'm going to cover why multiple implementations is important for a decentralized network like Filecoin, and especially for a blockchain. Then I'm going to briefly introduce the 4 implementations. If you have tuned in for earlier sessions in Liftoff week, you will have already heard about these implementations, and you would have heard from the developers themselves. So I'm not really going to focus too much into this. Then I'm going to talk about how we work together as a distributed team, as a global team, developing a single protocol. And then I'm going to focus on test vectors. And I'm going to focus on this fantastic tool that has been super useful to test the robustness, correctness, and adherence to the protocol. And then I'm also going to cover a few other tools that we've built around test vectors and that have been catalyzed and spin off from this project. And then also how you can get involved in all the fun. So the first thing that I wanted to make sure that we're on the same page about is why multiple implementations are important for a protocol like Filecoin. First of all, having multiple implementations allows us to ensure that the network remains robust and resilient in the presence of bugs, especially in bugs that are present in a single implementation. And when it really depends on the nature of the bug, but if the bug is in the protocol, if the bug impacts consensus, it would be immediately spottable in a network that is heterogeneous, that is running with multiple clients, that one particular implementation has deviated from the rest of the network because there will be a fork emerging. So this is really, really important to have multiple implementations, because if we didn't, then the bug would probably persist for a long time, because we would have potentially no way of noticing it until, maybe potentially it was too late. It is also important to have multiple implementations to make the network resistant to attacks that exploit a vulnerability found in a single implementation. So this is the same sort of challenge or the same necessity, but from a different angle, from the angle of security. So if a network, so it's really important for multiple implementations to have been built against the specification itself and not having copied each other a lot in the implementation details, so that potential security vulnerabilities in one implementation don't actually translate into another. So when we have a network that's operated by multiple clients, multiple implementations, if security vulnerability is found in one, it won't take down the entire network as a whole. It's also important to verify that the specification is clear, non-ambiguous, and implementable by a variety of developers coming from different backgrounds and different experiences, right? So as I said, ideally we want to implement these clients starting from the spec itself. And also, it's really important to have variety, because it allows us to onboard talented developer communities from different languages and have different focuses and skill sets. And this creates a diverse ecosystem, a diverse Filecoin ecosystem. And it also allows us to get many, many, many more eyes by essentially multiplying exponentially the amount of people that are looking at the protocol and the specifications themselves. So the quartet, the 4 implementations as they stand right now are Lotus, with which the network is operating right now. This is what we consider the reference implementation. It was developed by Protocol Labs, and it also works hand in hand with another project that we call Specs Actors. And this is kind of like the actor implementation that embeds into Lotus itself. We've got an implementation written in Rust. This is called Forest and is developed by ChainSafe. You would have heard from them earlier in the week, and they have a heavy focus on safety. And also they were the first ones to adopt test vectors, so kudos to them. And by the way, I just got news from Austin yesterday, I think it is, that they're successfully passing all test vectors now. So this is amazing. There's a third implementation called Fuhan. This is developed by Soramitsu, and they are just preparing to adopt test vectors. And by the way, underneath each of these implementations, you can find a link to the repo in case you're curious to explore them. And we've got another implementation that has just joined the group. It's called Venus, and it was originally Go Filecoin, which was originally started by PL, but it's now continued by IPFS Forest, and they're targeting interoperability in 1 month time. So that's amazing. If you're interested in implementing Filecoin from scratch in another language or targeting another environment, make sure that you get in touch with Protocol Labs at filecoin.io/grants and potentially apply for a grant. All right, so how do we work together? As I said, these are many organizations developing different clients, and we are all distributed across the globe, right? So there are a bunch of things that we do to make sure that we stay aligned. We implement or we propose, submit, discuss, and review protocol changes through Filecoin improvement proposals. These are called FIPs, and you can look at them in that link over there. We also get together every 2 weeks in a status call. We do discussion, we coordinate, and so on. And these calls are entirely public, so you can watch them on YouTube in the Filecoin channel. And also, of course, we interact as developers. We interact as through our usual channels. Man, what a day today! Usual channels. So GitHub, Slack, and so on. We also, of course, submit issues and PRs against the specs themselves. And also, we have this new set of tools called test vectors that allow us to verify our implementation. So I'm going to focus on that. All right, so what are test vectors and what is a test vector? So test vectors have been incredibly useful to get us all on the same page and to make sure that implementations are able to test themselves against a set of interoperable, declarative, and fully deterministic test cases. A test vector captures preconditions, inputs, values that are coming from the environment, which are stubbed, like randomness, and also that capture the expected output. So you can imagine that the component that is being subjected to a test vector is kind of like a black box, say, for example, the VM, the Filecoin VM. And the test vector tells you how to prepare the environment, what to feed as an input, and what the output should be from that black box. So this allows us to test the correctness and conformance with the Filecoin specification, and also the interoperability with other implementations. An important thing is that test vectors are never crafted manually. They're never written with fingers, right? They're always generated with tooling. They can be generated from ideally any Filecoin implementation. Right now, they're being generated from Lotus. And there's 2 ways to create test vectors. I'll talk about that in a second. Test vectors, you can think of test vectors as kind of like a thing that captures a photograph that captures what behavior that is true in one implementation so that it can be verified in other implementations. So essentially they serve as functional test cases to begin with, but then they survive as regression tests going forward. So some of the challenges that are addressed by test vectors is, first of all, we need a way to capture how a system behaves given a specific message or a specific tip set or a specific block, because the way that an implementation behaves should be exactly the same across all implementations. As we accumulate a corpus or a body of test vectors, it also allows us to catch inadvertent consensus breaking changes that we make to the implementation. So you can think of this as kind of like we keep adding test vectors and they keep accumulating. And the important thing about a blockchain is that you should always be able to sync from Genesis, from zero, right? If you really want to. So think of a blockchain implementation as the accumulation or protocol implementation within that blockchain implementation as an accumulation of all the changes and an aggregation of all the changes that have happened to the protocol all throughout history. Because if you want to sync from Genesis, from tipset 0, in the case of Filecoin, you need to be able to arrive to the same state at every single tipset sequentially, right? So this means that your implementation will accumulate all of these changes, and it's important that the test vector corpus is also storing and memorizing all those behaviors that were captured across and a long time, right? So test vectors allow us they award us with reliable, deterministic, and interoperable conformance testing. So basically, we write a test vector once, and we're capable of running it against all implementations. The alternative to this would be for each and every implementation to write the same test over and over again. And this also has been, having a body of test vectors has also been super important to avoid what I personally call big bang testing. When you're implementing a system from scratch, you're implementing a blockchain client from scratch, there are a lot of components that make a blockchain client, right? There is the network, there is the chain itself, there is the store, there is the VM. There are so many things that make up a client. If you had to build all of them to be able to start testing your implementation, it's kind of like paradoxical, because you're building the thing without being even able to test it. So having test vectors, you're having to build the entire thing without having been able to test like specific parts. So having test vectors allows us to target specific components as they're being built, and it also allows teams to parallelize their work. In the future, we also want to be able to attach test cases and test vectors to Filecoin improvement proposals. All right, so enough about kind of like the fundamentals and the motivation and so on. Let's talk about what a test vector looks like in reality. This is what you see on screen right now is an example of a test vector. A test vector, as we've implemented them in Filecoin, in the Filecoin project, there are JSON files, which makes them human and machine readable. And they are described by a canonical JSON schema file, which you'll also find in the repo that I linked to in the header slide. So that's it, Filecoin-project/test vectors. So a test vector captures preconditions, things like the base epoch, the network version, the state tree, the base fee, and a few other things. It captures the things that need to be applied on top of those preconditions, so things like messages, tipsets, and blocks, and it captures the post conditions. So the things that need to be true for the vector to pass, for the test case to have been considered successful. It also defines variants, diagnostics, and we also include the state tree and particular slices of the state tree as a base64 gzipped string in the vector itself. So the corpus of test vectors, which is the book of all the test vectors that exist right now, is composed of 850 vectors right now and counting. There are 3 classes of vectors. There is the message class vector, which targets the VM. There is the tipset class vector, which targets the mechanism by which the blockchain is assembled. And then we're working on a 3rd class, which is called the block sequence class. And that targets blockchain synchronization itself. As I said earlier, vectors are not typed in manually ever, and you probably saw why in the previous slide. They are generated or extracted. So we can generate vectors with scripts. We have built a Go-based builder DSL that makes this super easy, or we can reap them off real networks. So if we find messages or tipsets in mainnet or in other testnets that we want to capture in a test vector because they trigger a particular interesting functionality or an edge case or whatever, we have tooling to do that. And I'm going to demo how it works in a few minutes. So just to give you kind of like the bird's eye view of how we build the test vector system, on the left-hand side of this diagram, you see how vectors are generated. So as I said, generated by reaping them from a network or by crafting them using a DSL. And on the right-hand side, so these two things actually create vectors. And then VM implementations and Filecoin implementations, all they need to do is implement a driver that is going to consume that test vector and subject their components under the circumstances and situations described by that test vector. So just to give you an example of how a test vector is built in the generative way, so this is crafting it using the DSL. This is a simple example, which basically sends a transfer from an unknown sender and a known receiver. And what we are testing here, so there's three phases. There is a precondition phase where we create the accounts and we create the state tree on which that vector is going to run. Then we create the applies, so the things that are actually going to be applied. So in this particular case, a transfer. And then there's a third stage, which is the assertion stage, where we verify that certain conditions are met. And one important thing is that the protocol evolves over time. So each of these vector scripts don't just generate one vector, they generate many vectors. They generate a vector per each known protocol version. So Genesis, Breeze, Smoke, Ignition, Actors version 2, if you've been following the history of the chain now, these terms will be familiar to you. And we also have a mechanism in place to coalesce and to merge vector variants that are identical in their preconditions, postconditions, and so on. There are certain conditions that we wanna be able to test that are not present in the production code, but we wanna isolate and be able to test specifically. And to do that, we deploy a special actor that we call the chaos actor, whose role is exactly that, to wreak chaos, right? Vectors that use the chaos actor have a specific selector enabled, and the chaos actor allows us to trigger illegal actions and also concrete actions that are not normally found in normal actor code, like minor actors and storage power actors and so on. And this allows us to, in this particular case, isolate the VM runtime and test it separately. Another way of creating vectors, as I said earlier, is to extract them off a real chain. For this, we have a tool that's called TBX. So this is test vector extraction tool, and it lives under the Lotus repo, under that directory. So in case you're curious, you can take a look. And it allows us to basically cherry pick a message from the chain and generate a test vector out of it. And it does some interesting things. If we were to, so say, for example, right now the chain is at height 170,000 or something like that. If we were to have to extract the entire state tree to be able to run one message, that vector would be gigabytes big, right? So we can't do this. So what the tool does is it masks the state tree, filters the state tree such that we only retain actors or CIDs that were effectively accessed during the execution of the particular thing that we're applying, whether it's a message or a tip set or whatever. And I'll show you a demo of how this works in a few minutes. Now, one thing, so you saw what the test vector looks like. It includes a lot of binary data, and the state tree is not precisely, let me just rewind. So this is, so where you see the car here, the car field, that is kind of like the state tree, and it goes on for a lot more bytes than that. So it's not really immediately obvious what's going on inside a test vector. So if you apply a test vector and it happens to fail because the post conditions are not met, you need a way to be able to dig into what that vector expected and what is it that your implementation actually generated and how it deviated, how those two things deviated from each other, right? So we created a tool to go along with this entire suite called StateDiff, and it uses a library called GoComp along with IPLD schemas to traverse and recurse the state tree. And it has two modes of operation. Given a car and two root CIDs, it can compare the state trees anchored at those roots inside the car. A car, by the way, is a content archive. So it's basically a way of storing an IPLD repository inside a file. And it also has a second mode of operation, which is given a vector, compare the precondition and the postcondition state trees. My colleague Will Scott, who has been working on state diff, and he basically owns all of state diff, is going to give a talk later. So make sure that you tune in, because it's super interesting what this project is doing, and as well the other tools that that state diff has catalyzed, like State Explorer and State Dump, and he's going to cover them later on. So, of course, we've been talking about testing, and there is a lot of course, it would be completely useless if we weren't actually running those tests. So all our test vectors are running continuously. Right now we have 2006 tests that are passing. So these are test vectors that are run for all the variants against all the network versions that they specify. And this is run for every single build on the Lotus CI. And as well, as part of that build, we're generating detailed coverage analysis. So we are able to see what parts of the code are covered by test vectors. And this way we can discover and identify parts that we should extract or create test vectors for. So ideally, the dream is to reach 100% coverage, but who doesn't have that dream? And as I said earlier, this screenshot is outdated because it shows only 564 test passing, where there is a lot more now, so 800 and something. And this is a screenshot from the Forest CI running the test vectors. Right now, they're passing all test vectors, so kudos to them. That's amazing. There are other tools that kind of like surround this ecosystem of testing within Filecoin. State diff and state dump already covered state diff. What you see there is it's a screenshot of State Explorer. This slide should say State Explorer, which is a project that Will is going to talk about as well in a few hours. And then we also built, so if you've been following kind of like the developments in projects at Protocol Labs, you will have seen a project emerge a few months. I think we launched it in May this year, and it's called TestGround. And this is basically a platform to allow us to test peer-to-peer and decentralized systems at scale. And we've iterated on top of that to build what we call Test Run as a Service, which is a continuous testing facility. And Anton, by the way, Anton is gonna cover this as well. My colleague Anton, we've been working together very closely, is gonna cover Test Run as a Service in a few hours as well. So make sure that you tune into to that one. All right, so it's time for demos. I'm gonna show a few things here. So I wanna show, first of all, running conformance tests on Lotus. Then I'm gonna show running a single vector. Then I'm gonna show extracting a test vector. And I'm going to show state diff, and I'm going to show state diff in two different ways. So just going to do some window moving here, and there it is. All right. Okay, cool. So the first thing that I want to show is running the conformance. So within Lotus, in the Lotus repository, there is a Git submodule that imports the test vectors. And inside the corpus directory, you will find all the test vectors here, right? So the conformance package in Lotus runs the vector. So I'm going to run that suite, and right. So that's it. All right. So you will see an output now that is basically an entry for every test vector that the VM and the implementation is being hit against. And there you go. You can see that there were some log lines there where we were replaying randomness from the test vector into the VM. This is usually important for test vectors that have been extracted from chain. Right, and you get the gist. I'm not going to wait until the end, but it takes around 50 seconds or 60 seconds to complete. And this is 2006 test cases that are running. So the next thing that I wanted to show you is, if I'm able to get my browser opened, right. So we're going to pick a message from chain, and this is Phil Fox, is one of the many blockchain explorers that exist in the Filecoin ecosystem. So I'm just gonna go a bit behind to a previous tip set, like say, for example, this one, just in case my client is not synced entirely. And I'm gonna pick the first message on this tip set. Say that there's something special about this message that I wanna memorize into a test vector. I'm gonna pick that one. So, so tool is here, right? So I'm gonna replace the CID of the message by the CID of the message that I just picked from chain, and then I'm gonna add one of the blocks where this message is present in, and this allows us to go into that message very. Oh, my blockchain, my client has fallen behind, so I'm gonna look at where my client actually is. So that's in 984. So, oh, it's quite far behind. All right, gonna have to look into why that happened. Let's go 984. 984. So let's go into this one, 980. Let's pick a message from there. So from this block, I'm gonna pick this message instead. So I do tvx extract CID. This is the message, and this is the block, and there you go. So what this is doing is it's recording, so it was very fast. What this is doing is it's basically finding any messages on that block that were sent by the same sender. And then if there was 0 precursors in this case, and then it's reproducing that message, recording randomness, recording beacon and chain randomness, and also the sets that were effectively accessed. And this is the vector that it outputs. I've saved, I'm gonna do it again, but I'm gonna save it into vector.json. So you will see that the vector is here, right? Another thing that I wanted to show you was executing a particular test vector. So this is a test vector that I wanna execute against this implementation. TVX has a command that allows us to pick a vector and execute it against the implementation. And this was really, really quick. You can see that the vector succeeded for the Genesis fork, for the Breeze fork, and for the Smoke fork, and for the Ignition fork. So imagine that now I wanna have a look and see the differences in that test vector that we extracted earlier from chain. I wanna see what things in the state were effectively altered by that vector using state diff and using the vector subcommand and providing the vector, which is this one over here. I should be able to see that. So state diff, there you go. We're going to do a color diff to get a better output. And you see that this particular vector is changing the balance, is changing the nonce of a particular actor, and is changing a few other things. As well. There is a little error there about a thing that wasn't able to resolve. We should probably fix that. Let's see, do I have another interesting thing to show you? Yeah, so say for example, I have a test vector here that has been extracted from chain as well that initializes a new actor on the state tree. And this will have an interesting diff because it will show us a new actor being created on the, oh, sorry. So this should be on extracted, right? Let me change the path there. So this is extern and test vectors and corpus, and there you go, right? So you see that we also have nonce changes and some other changes, but you see that we have a new actor being created here. So that is consistent with what the vector is doing. Of course, if a vector fails at any point in time, we automatically print the state diff inside our CI jobs. All right, so just before I wrap up, I wanted to talk about the future of test vectors. We are working on new TVX tooling to simulate test vectors and to project test vectors. So simulate allows you to take a message and simulate it on top of any tip set and explore what that message did to the state via state diff. And then we're introducing another command called project, which allows us to take a vector and project it against new protocol versions. We're also introducing a new class of vectors called block sequence vectors, which basically define a sequence of blocks that arrive at specific times against the sinker. And at the end of it, the post condition is that the head of the chain should match a particular head. This allows us to test potential fork emerging in potential forks emerging in the network. And also, of course, we're enhancing vector coverage. So just a few notes. If you were intrigued by all of this and you would like to contribute to making Filecoin better and to make sure and to contribute to making Filecoin more robust and better tested, if you find an interesting, problematic, or unique message on chain that you want to capture and memorize, then you can extract a test vector. Also, another way that you can help and contribute is by exploring the coverage analysis on CI, finding messages on chain that trigger uncovered code paths according to that coverage analysis and submitting them onto the repo. And also a tip and kind of like recommendations to fellow implementers, make sure that you contribute test vectors generated from your implementations, and also contribute test vectors where consensus between your implementation and the Lotus implementation or another implementation diverged. And also a very important note, we have just started a bug bounty program for security researchers to identify security issues. So make sure that you use test vectors if there's a particular behavior that you find that could be attacked, exploited, or whatever, and you want to submit it to be eligible for a bug bounty. Then a really nice way of making that submission would be to capture that input that provoked that security vulnerability to trigger as a test vector.